Okay, 918. And you're saying it wasn't challenging, so you got to be missing something, so that's why you want me to look at it. Oh, you don't know how to do it. You're not supposed to admit that. That's too honest. All right, so for a 50 by 2 NMOS device in the short channel process, show that the GFT of the device does not vary with overdrive voltage by using simulations to plot GFT against VGS. Okay, so I'll tell you how to do this, and it's not going to be perfectly flat. You're going to see some variation, but I'll show you how to present the data. So you can't in the simulation just real easily plot GFT versus VGS, right? So what I would do, because the simulations are already there for chapter 9, is I would take and I would simulate the FT, and I would go also simulate the GMR out. And so this is the open circuit gain, this is the speed, and then I put that for a VGS, and I'd write the numbers and I'd do the simulations for each one, and I'd vary VGS. And then I'd take this and I put it in a spreadsheet in Excel. Okay, and then I would plot these two times each other in the third, so you could put a third column here, GFT. And I would plot that GFT versus VGS in Excel. How's that? So it's really not a challenging problem when you think of it. It's just plugging in the numbers, writing it in, and then plotting it out. But it does get you to see how GFT changes with VGS, and it's not going to change drastically. Okay? Any other questions? You had a question? Okay. Was there anyone on this homework? Okay, so what was the one for the one that was due today? All right, so no question? Okay. Lay it on me. How do you, is it this one? Oh, the one due today, sorry. Everybody, I put this on here just so you would know. Monday, February 16th. And let's see, today it was the 15th, all right? So let's look at that. Repeat problem 919 on 309 for the PMOS device. Show how the schematic, the PMOS FTs. Okay, so this one is I already did this. I put it in the LT Spice examples. Oops. Right here. And which one is it? It's what number? 31. So there's a 31 PMOS. So this shows how to plot the FT. Whoops, that's not 31. And 27, forgive me if I don't believe you. 34. So 34 PMOS right here. So you plot ID versus, and so it's already done. So that's how you do it for the PMOS. Is that the question? All right. So, I put all those resources on there to make it easy. Okay, any other homework questions? All right, so let's move on to chapter 20 and talk about current mirrors. And this is our first analog circuit that we're going to talk about, which is the current mirror. And you've kind of seen it already before, but I want to go through it and give you some intuition before we get into too many different topologies, because there's all kinds of different flavors. So let's do the following. And this, I want to just also point out that current mirrors only work with integrated circuits. You can't go into the lab and grab 2 transistors and then go to the little white proto board and put the 2 transistors and form a current mirror, okay? Because they have to be perfectly matched devices. The exception to that, where it can kind of work, is if you get date codes from the transistors where they're fabricated in the same process run. So there's a date code, something, if you look on the transistor, it might be like, I don't know what a good number is, like 2001-32 or something like that, which means this transistor was fabricated in the 32nd week of 2001. Okay, then those transistors are from the same wafer, but there's still issues there, okay? Because I remember back in the day I tried to make an op-amp using transistors, discrete transistors, and it didn't work very well. And so that's why. So I just want to keep that in mind. So if you try to do like power MOSFET current mirrors or something, it may not work. Okay, so a basic current mirror looks like the following. And we're going to go over the qualitative, or not too qualitative, but the operation here real quick, because I want to point out some real key points. In all of these topologies that we talk about, what we care about is the VGS. Okay, right here, that's what controls the current. So when I look and say, is this current equal to this current, I look and say, are their VGSs the same, and are their W over Ls the same? And we'll talk about that more in a moment. Now I'm going to sketch, let's just put a current source here. We don't know how we implement that. But I'm going to sketch that driving this, this transistor here. Okay, and if I do that, this is a good thing to plot. If I put a specific current here and I were able to change the W over L or change the VGS somehow, I would get a curve that looks like the following. Okay? Obviously, this transistor, assuming it's the same characteristics, is matched to this one, correct? So it's going to follow this same curve. But now notice, if I change the VDS across that device, I'm going to move from here to here. Does everybody see that? Okay, so if I ask, okay, how do I get good matching between this reference here and this transistor here? You also, besides having the VGSs be physically the same, you also have to have the same VDS. So that's one of the key points in analog design. And as we start designing circuits and we try to get good matching, we're going to see that unless this VDS is the same as this VDS, the currents aren't going to match between the two sides. They're going to be close, we're going to approximate it, but they're not going to match. So say this one has a higher voltage, it's up here. This might be 10 microamps and this might be 11 microamps. We're going to say they're the same for analysis, but if we ask are they precisely the same, we'll know this one because it has a higher VDS, conducts a little more current. Does everybody follow that? Okay, so another key thing. You see this point right here? That point will often draw schematics that look like this. And we'll say this, that point is this point right here, and we'll assume when we have a current source that we have this transistor connected between here and ground, here and ground. Does everybody see that? Okay, so now the question is, how do I relate the two currents based upon the W over Ls? So I'll call this M1 and this M2. I'll call this ID1 and this ID2. And just as a side note, you might ask, well, wait, how do I actually generate this? This point and this VDD would come from a transistor which is biased like this. So this point and this point would be the same, and then this transistor would be replaced with that current source. Okay, so I got a question. Ideally, what is the output resistance here of this guy? If I were to draw the ideal current source over here, what would it look like? Yeah, just be a horizontal line like that, right? Like this. We did that right in the first day of class. Okay, so ideally, the output resistance is infinite. Does everybody see that? But in reality, it's not. 1 over the slope is the output resistance of the current mirror. So instead of having a current source like this, we would have a current source like this, paralleling our resistance at parallel. So it'd be imperfect. So one of the things we're going to do in chapter 20 is we're going to take and we're going to add extra circuitry above here to try to pin this voltage at a fixed value and try to increase the output resistance so that the current source behaves like a ideal current source. And when we do that, we're saying when we try to increase that resistance, we're saying that we are increasing the output resistance of the current source. Does everybody follow that? Okay, so one more thing. You see how right when we get to this VDS right here, what happens? Kobe, what happens? Okay, I know, but see, the thing is, I want you to understand, I'm not talking to you because I don't care. I do care, okay? That's what you need to understand. What happens when the current source goes into this region right here? If I decrease the voltage here, I start driving it towards ground, what happens to the current in here? If I start driving this voltage towards ground, what happens to the current in the source? It goes to zero. Does everybody see that? So now, if I look at this and I say, all right, well, what is this voltage here? That's my VDS sat. That is the voltage where the current source shuts off. That is called, and this is another one of those buzzwords, the compliance range. So if I ask, what's the minimum voltage across here, like for, let's say in our 1 micron process, we had 1.05 volts and our threshold voltage was 0.8, so the difference is 0.25. When we get to 0.25 here, below that, this starts to triode and shut off. Does everybody follow? Okay, so that's the minimum voltage I need across there is VDS sat or V over drive or V excess. Okay, any questions? Is it all making sense? Okay, so I have ID1 over ID2. I'm going to look at that ratio. I'm going to write this transistor as W1 over L1 times Kp sub n over 2 times VGS minus V threshold n squared. That's all divided by W2 over L2 times, Kp sub n over 2 times VGS minus V threshold n squared. Does everybody follow that? So what do you notice? Yeah, boom, boom. And I can write here ID1 over ID2 is equal to W1 over L1 times L2 over W2. Yay or nay? Okay, so now if I were to, okay, so there's a lot of things here I need to point out, especially if you go get a job nowadays. This is useful in the older, like the processes we're using. You can increase the W's or change the W's and L's and influence the current that flows. Generally, the same L is used for several reasons. One is when you change L, your L, remember the MOSFET? Here's the device. And then you change the L here. Well, this lateral diffusion subtracts from the overall L, and then that changes what the effective L is. Does everybody follow that? So if I start varying the L, one L might be, if it was 1 micron and I had a lateral diffusion of 0.2, then it would be effectively 0.8 U, and then if I use 2, it's 1.8 U. Well, the ratio isn't the same, right? Does everybody see? So when you do design nowadays, you generally use all the same L's because of the lateral diffusion and because of the things we talked about on Wednesday, the speed and open circuit gain and all that. You don't start varying the L's all over the place because then that lowers the quality of your design. Does everybody follow that? One other thing, I had, and it's been a little while, but I had a former student email me and he says, I need to make a current mirror that in a nanometer process that is an integer ratio, is not an integer ratio. So you can't, in fact, I'll show you the comment, I posted it on the book webpage. Let's see. See, let's do a Control F, current mirror. All right, how would one implement a current mirror with good non-integer ratio and good matching? And so there's tricks to doing this, but basically in these modern devices, like if you go get a job at Qualcomm, these modern devices, you have to use the same sizes over and over again, all right? So you use these tricks like this W2W, you can click on the links if you're interested, that will split the current up and basically allow you to sum the current so that you get the right values. All right, and so the key point is that you just can't, and I tell you this because probably none of you, unless you're doing biomedical design or something like that, none of you are going to design in the older processes, or automotive electronics do design in those older stuff too, and so do a lot of sensors. Okay, I take that back, maybe you will get it. All right, so if you don't have that, you can't adjust these two. So basically if the L's are the same, you get W1 over W2. So if I make this width twice as wide as this width, then I'm going to have twice as much current flowing in here. Does everybody follow that? Okay, are there any questions on how to do this design? Okay, so I got a question. Let's take a basic current mirror. Let's look at figure 20.1. And I've got a resistor. Okay, so this is a real circuit. This is something you would build. And I have a device like this, and let's just put it going to the power supply. And I take that, and let's just assume the same size devices. We'll call this M1. We'll go over here, and this will be M2. And I ask you, okay, well, let's ask some simple stuff to begin with. Well, let's ask some real simple stuff. What do I think of this point as here? It's a current sink, right? I think of it in my mind. I might be lazy and draw the current source just like that because that is how I implement a real current source in real life. No longer we're drawing this and it's just magically a current source. Now I know how to implement it. Okay? All right, so that's this point, that's this point. What do I know about this current source, though? Let's name two things. One is the minimum voltage I can have across it. What's the minimum voltage I can have across here? VDS sat. VGS minus V threshold in. And I'm going to write this out because it's confusing. That's VDS sat, or could be V overdrive. Any questions? Okay, what is, if I wanted to accurately model this though, what would I also add? A resistor. But I'm not going to do that. I'm just going to know that the current sink is imperfect. Okay, does everybody follow that? Okay, so now, I know these VGSs are the same. Let's assume I have the same device sizes. They control the current that flows up there. What is it I know about this value? What if I want the currents to be precisely the same? I'm designing a digital to analog converter to drive the display of my cell phone. You might say, well, what does that have to do with the current mirror? What it has to do with is that's what drives the cell phone. It converts an analog current to drive the LEDs or whatever this is in the screen through a digital to analog conversion by weighted current sources. So you put the digital word in there, it sends the current to the display, and how much current or how little current changes the illumination in the red, green, and blue pixels. So let's say I wanted to have good resolution so I could zoom in on the pixels and see the difference between, you know, the edge of a star and a dark sky or something like that. What would I do in order to have good matching? Yeah, I got to match the VDS. So can I just leave this open and say it's a current source? No, I got to connect it somewhere, right? So I'm going to make a mistake. I'm going to come over here and I'm just going to connect it to a resistor like this, R. Why doesn't that work? No? Think about it practically. Okay, it's potential related, but where's the water flow? Water flows from a high potential to a low potential. What's that? Yeah, there's nowhere for the water to flow down. This is a drain. This is a drain. It's like you in your bathroom saying, hey, I have a drain beneath the faucet and I have another drain at the bottom of the bathtub. How come no water's flowing? There needs to be some pressure, some potential. So I need to have a connection up to VDD. Now, if I want the exact same current to flow on each side, I want to put the exact same resistor here. Why? So the VDSs are the same. And then the current flows. The key point is, this is real life. I can't get a current source if I don't have a potential for this to supply current. Does everybody follow that? Any questions? All right, so let's actually I want to do an example. All right, and let's just make a simple example. Let's pick one with PMOS current sources instead. Yes.
So what's the point of setting up this mirror if you have to basically replicate exactly what's going on earlier? So what's the benefit?
You get a current source. And so what you can do with the current source is, here, I'll give you a simple example. We'll do a 3-bit digital to analog converter. Okay, so here we go. I build this on the chip. And if you took 421, 621, you know how to do this already, all right? So let's just say using this process, I have a 10 micron by 1 micron device. This is 5 volts. And let's say that I put a resistor here of 200K to ground. Then I go over here and I've got a plus 5 volts, and this is 20 by 1. I go over to the next one. This is 40 by 1, and you know what, actually I'm going to put one more in here of 10 by 1. Okay, so before I go, this notation, this gate and drain are tied together. These are all tied together, so the gates of every one of these transistors are tied together and their sources are all tied together. Okay, in the olden monitors, the old monitors, the CRTs, if you measure the input resistance, it was 75 ohms. So there would be a 75 ohm input, and you would feed a current from your graphics card with a technique just like this to those 75 ohm inputs, and they would be differential. In other words, you would put differential current, so one would be going up, the other would be going down. So here, if I tie all three of these together, this current is the same as this. This current's twice as much as these, and this current's 4 times as much. I could put MOSFET switches in here. We'll just do it like this. And I could call this B0, B1, and they're active low, and B2. And then I could turn these switches on, just use them as digital switches. So if you haven't taken digital, the way you think of this, when it's a switch, not an analog circuit, is this node, the reason there's the bubble there, is it goes to 0, it turns the switch on. So when it turns the switch on, the current source is connected to the 75 ohms. So if I have 3 zeros, then I have all 3 currents coming down. If I have this as 0 and these 2 aren't, then I just have this current going down. Does everybody see how the circuit works? Very practical digital to analog converter. This is the way it's done. So this is one reason why you would want current sources, but we'll use a bunch of other ones in the class when we make op amps. Okay, so what we need to do, and you'll have a quiz on this probably on Wednesday, is I need to calculate the current that flows in this transistor. So this is one where you need to solve a quadratic equation. So I'm going to take this part, and then I'll calculate VGS or VSG and the current. And then once I've done that, I know this will be the same current, this will be twice, and this will be 4 times when I'm neglecting what? Output resistance. There's no body effect here because the body is tied. They're all sitting in the same end well. Source and body are shorted together. Okay, so once I calculate this current, then I know what the other currents are. And I know what the LSB is of the DAC. What's the LSB? Least significant bit, and it's this current, right? And if I want it in terms of voltage, what's the least significant bit? This current times 75 ohms. Challenging. All right. So I have this. Ten to 1. And we're going to, since you need to know how to do this, I want to go through it slow this first time, but then we're going to do it over and over again for different topologies and probably on your homework as well. Tell me how to start. What's that? Well, let's label. This will be VSG. This will be ID. So I'm going to write a loop. Tell me what to do. Yeah, it's in saturation because the gate and drain are tied together. Let's write that because I'm learning. Drain, source. Five minus VSG minus what? Yeah. Anybody not follow that? Now, what's the next equation I'm going to write? And I remember Kp sub P is equal to 40 microamps per volt squared. V threshold P is equal to 0.9. No problems so far? Going to get 100 on the quiz? Okay, so then I'm going to plug this in here. And I'll write 5 minus VSG. And then I'm going to write this as 200 micro times 200K. Let's simplify our lives. 200 E6 change sign times, whoops, I already made a mistake. That's, oh no I didn't, that is 200, right? 200 E6 change sign times 200,000 equals 40. Does anybody want to second that? Alright, so I'm going to just go ahead and write this out as VSG squared and then minus 1.8 VSG plus, yeah, you know when you don't answer, I'm like, do they know what's going on there? Any questions? All right, so let's go ahead and multiply through. So I get 5 minus VSG minus 40 VSG minus 72. Eight times 4 is 32. 0.1 times 4 is 0.4, so 32.4. Positive, thank you. Don't want to get the quiz wrong. And I probably should have just divided through by 40. Oh well. And so then I can write 40 VSG squared. I'm going to multiply through by minus. And then that would be minus 71 VSG plus 27.4. Of course, you probably have one of those fancy calculators that does roots. I don't. I have the old Casio. All right, and what's the quadratic equation? I solve for VSG. Opposite of b, 71 minus the square root of b squared. Opposite b plus or minus the square root of b squared minus 4a, which is 160 times c, all over 80 over 2a. No one's challenged by that, right? Let's make sure I did it right, though. Opposite of b, plus or minus the square root of b squared minus 4a. Okay, I assume that's right. So why don't I just pause and write this in here as VSG equals 71. Did I tell you I'm not going to do this too many times in the future? I'll do it this one time so yeah, it's hard. So 71 squared minus 160 times 27.4 equals, and then square root 25.63. And I'm going to pause here and ask you to think about for a second, is it going to be the plus or the minus that's the answer and why before I solve it for the very end? Okay, if it's the minus, just do a quick calculation in your head. VSG is, say, 50 divided by 80, which is, say, half a volt. Is that correct? Why? It's less than the threshold voltage. So everybody follow that. Okay, so I got to use the plus. So I'll go ahead and write in here VSG is equal to plus 71 equals divide by 80 equals 1.207. Any questions? Because I want to continue and show you where not to do. Yes? Yep. Yep. It might be that you end up with a VSG that's 6 volts and the other one's 1.2. And you know it's not 6 volts because that's greater than the power supply voltage. Any questions? Okay, so that doesn't tell us, that tells us what VSG is. It's 1.207. But it doesn't tell us what the ID is. So now I don't want you to make mistake on the quiz. What you don't want to calculate ID is plug it in here because that's extra work, right? The way you want to calculate ID is you want to say, oh, this is 5 minus 1.207 means this voltage is 3.793. If I did the math right in my head. Does everybody see that? So then I go, oh, it's 3.793. Then ID is equal to 3.793 over 200K, which is equal to 18.96, so roughly 19 microamps. Any questions? I've got a question. Do you want me to simulate this circuit? Because I'm thinking that it's straightforward, but if you want me to do it, we'll do it real quick. You do? Are you sure? I know you don't think I can do it. That's the problem. Yeah, we'll do the whole thing. Okay, so let's go and get in here. Should I do it from scratch again? Oh, come on, man. All right, I'm telling you we're not going to waste time on this pretty soon. This is lecture 7, 8. You realize we're 2 lectures ahead? I'm going to keep going like that. By the end of the semester, each of you will get a bill. Just joking. It's funny the way I think of education, but I do think of it in terms of business, and yeah. All right, so let's go grab our PMOS 4, And then if you recall, for some reason, LT Spice puts the source at the bottom. You don't need to do this because source and drain are interchangeable, but I'm going to do the following so that the source is at the top. Now I've done this 3 times now, so and I don't want to feel pain, so I'm going to copy this MOSFET as much as I can. I'm going to call this 1U, not 1. That's where I'll inflict pain on myself. And then I'll call this P underscore 1U. Oops. Underscore 1U. And just to make sure that I know that's the right name, let's go look at the models here, CMOS EDU models, and it's P underscore 1U is this 1 micron model. Does everybody follow? Okay, so then I go, and it's in the same directory here. So I'm going to go right click, control, and I'm going to double click this so I can see the size. Then I'm going to go grab, hey, let's wire up a little bit here first, or actually let's do this. Control E, flip it this way, and then I'm going to wire it up a little bit. And then come up here, and then I'm going to go grab a source. And I'm going to grab this here, and then I'm also going to put a source here because that's easy for me to look at the, I guess I don't need it because I have MOSFETs. I'm going to right click on this, give it a value of 5. I'm going to call this VDD because I like nice looking schematics that I can copy in the future. Press G. I know I'm going to need a ground here, so I'll go up now and connect this up just like that. Go here and then come down, and what is this node here called? See in the lower left it says node 001. I don't like that, so I'm going to change that to VDD. So now its name is same as the voltage source. Okay, any questions? Then I'm going to go get the copy and copy this. And I'm going to copy it again. Then I'm going to wire it up. And then this one I'm going to change to, don't worry, I'll flip them. Give me a second. 40. Okay. And then I'm going to get, you know what? I should have flipped them first. Yep, so we'll do this. Control E. This is fast. I'm fast. I was thinking how slow I'm going. I'm boring everybody. All right. You know what? I'm going to do this so everybody sees that I could go and connect the schematic up like this. Does everybody see that? What's another way of doing this? I could label this voltage V bias P, and then I could put V bias P over connected here, right? How many people keep thinking about the resistor? All right. So we'll go like that, and then we'll go here, 200K. And then we need a dot include, and since the models are in this directory, I can just put CMOS EDU underscore models dot txt, plop this down, and then let's do a dot tran, and let's go 1 second, make it easy. Let's put this here. Actually, let's put this up here. Okay, hit save. Any questions or comments? All right, so let's go run. And then let's go here. Boom. Oh, that's about what I calculated. It's off a little bit, but I expect that because my finite output resistance I didn't take into consideration. what should this current be? More or less, and why? Here, let's plot this current instead so it's positive. Should it be more or less? Should be about the same, however, oh yeah, sorry. What's this one then? About the same, but more or less, and why? Slightly more because it's got a larger VSD. Yep, no resistor. So we look at that and go, oh, it's at 22. And I know if I go grab, just for the heck of it, if I go copy this resistor and I put it in here and I rerun the sim, they're exactly the same because the VDSs are the same. Does everybody follow? Okay, so I come down here. I'm going to get rid of that. Rerun the sim because I want to do one more before we quit here, or before we do the DAC, because I want to show you that the DAC actually works. And run it. And then, okay, so here's the current here. Here's slightly more. Whoops. Then here's roughly 40. Well, that's even higher. Why? Give me another reason based upon what we covered why this would have even more current. It has to do with the, remember there's also a lateral encroachment, or a oxide encroachment on the width, so that subtracts from the W. So this W will be, if it was 0.2 microns, this one would be 9.8. This one would be 19.8, so it'd be slightly wider W, so you'd expect even more current. And then that's why all these things, you have to look at the secondary. Oops, wrong one. Let's get the scissors out and cut that. This one. Does everybody see what's going on, and is anybody bothered that the currents aren't exactly the same? Okay, so I want to save this sim, so we got it, and then I want to go do the show you a digital to analog conversion, then we'll move on. Yes? To make an ideal current source? Yeah, you want to have the output resistance be as high as possible, but it's inherently limited by the transistor. Now we can increase the L's, and they'll get more ideal. Okay, but if we increase the L, what do we do to our speed? Yeah, it goes down. And so there's trade-offs. Yes? Is it possible to... the hand calculations in the nano CMOS are tough, so that's why we generally use charts. So a plot like in chapter 9 in the end, like those page 30 or figure 32, 33, 34, and you get the charts. And when you go to a company, they have a manual that describes the process. And so then in the process, the manual will have all the charts, and so you don't do hand calculations from like the square law stuff we're doing. It's more reading off the charts what the values are for the parameters and then simulating. No, I mean you try to, but it's hard to use the square law models for the modern stuff. The problem is, you might ask, well, why would you teach the old stuff? And as I mentioned earlier, still the old stuff's the cheapest to fabricate in, and there's still a lot of designs, medical, automotive, things like that, that are done in the old stuff. But also when you're teaching a university class, you have to make sure that you have practical and that stuff balanced with a little mathematical rigor so that you do calculations. So that's why there's the two-path approach. All right, so let's close this, and then let's open it back up. And let's show you, because I just want you to prove I like it to see things where I know, oh, I actually learned something. And I know 20 microamps is not a lot of current, so if I put that into a 10K resistor, I would get 200 millivolts. So what I'm going to do, I'm going to grab a resistor here, and I'm going to make that 10K as my load. I'm going to plop this down here. And now I'm going to go delete these. Now I'm going to copy this transistor here. Oops, God, I have a bad habit of that. Let's save that as example 2. And because I do the same thing when I make up quizzes, I'll open up an old quiz and then I'll start typing without saving it. And then when I realize I hit save and I've lost the other quiz, I'm like, dope! All right. So let's go copy this. And I need a switch. So I'm going to go here, copy, copy, copy. And I'm going to change the schematic to look a little more pleasing. The way it would look if you were drawing it in industry. So all of these are together. I got a question while I'm drawing this. If one of these shuts off, no more current flows in the current source. Is that bad? Does that influence anything? No, it doesn't influence anything. I still have the VSG there, right? But I don't have the current flowing in that branch because the switch is off. Okay, so everybody knows these in my mind I'm going to think of as switches. And actually, you know what we're going to do to make the schematics look pretty, even prettier? We're going to do the following. Get rid of that. And then let's go copy. Oh, crap, I forgot. Let's get rid of this one too. Are you sure these simulations are good? Because they eat a lot of class time. Wouldn't you rather just take my word for it? I can do it, trust me. Okay. So now I'm going to come up here and I'm going to call this V bias P, just some voltage or some name. Let's stretch this over a little bit. All right, so if I right click on this, what do you think is going to happen? I highlight. See, it's as if all of those were tied together but the schematic. And so oftentimes when you read papers or you look at schematics from industry, they don't run wires all over the place because it's hard to look at the schematic. They'll use labels like this, all right? Now I'm going to go ahead and put on here, because I need to toggle, I need to put in a code B0. And I almost made a mistake. And then I'm going to come over here, call this B1 and this B2. And I could put sources in. You want me to put sources in or you want me just to write the code? Write the code? Source? Yeah, well, let's write this, let's put the voltage pulse in. So advanced pulse, I like writing code better. So we'll go 0, 5, whoops, starting to write the code right there. 5, 0, let's see, I'll just put 1 millisecond, 1 millisecond, T on. Let's go, how about 0.125 milli, period, 0.25. Oh, wait, let's not milli. What's that? And then let's go connect this up. Call this voltage. I got to start with the VB 0. Is anybody not following what I'm doing? Does anybody follow? Okay, so there's my B0. So this is a pulse, 0 to 5 volts for one, it's high 125 milliseconds, periods 25 milliseconds. Okay, actually, let me think about that for a sec. And we'll just simulate for 2 seconds instead. We could go faster just to show you, but I put it like this. Okay, so let me copy this. And let's change this to VB2. Or whoops, it was right and I blew it. Okay, and then call this VB1 or B1. And if I right click on that and say highlight net, it should highlight this. So we need this to be 0.25 and 0.5. And then one more and we're done and we are ready to go. Yeah, yay. And then we hit full and B2. Notice how I started at B0 and it's automatically incrementing. Oh, I guess I did do that right. Shoot. Oh well. We'll show 2 cycles. Okay. Any questions? Let's get the little hand here, pull that up. Right click on that. Highlight. Let's try it again. Highlight net. So everybody see it's connected. So when B0 is a low, this switch is on. And when it's a high, this switch is off. Any questions? Okay, so let's go and hit the V out. Save, run. Let's see if our B0s, this looks right. Then B1. Let's show you a trick. We'll go +6. And then B2. +12. And then we'll come down here, or I'll go here and I'll say add plot plane. And then I'll come down here. And there's our digital output. What are these glitches? Yeah, it's when they're changing states, when one's shutting off and the other's turning on. And how would I get rid of those in a practical circuit? Well, I could change the delays, yeah, and adjust them so one's on and one's off. But I could also just add a little bit of capacitance here, and it would smooth it out. Okay, any questions on this? I hope I've set the motivation that current mirrors are important, because we'll cover a couple more things and then we'll call it a day. No quiz. Is everybody bummed? You are? Well, you have to keep in mind I pick levels here. The transition times are 1 millisecond. There's not 1 millisecond edges. They're going to be like nanoseconds. And so if I change it to nanoseconds, the glitches will be tiny. However, I'm just trying to show you an application. So just so you don't think we're learning this is not useful, you know, you're using every time you pull out your tablet or you watch a movie or you listen to music, you're using a digital to analog converter. Okay, it's very practical. They're everywhere. All right, so let's not do any more simulations today. Wait, you know what? Did I save that? Crap. So let's do that. Boom, boom, boom. +6. I'm a neat freak and I like to close stuff. And, whoops. What did I do? All right, so we'll hit. Yeah. Oh. And then add plot plane. I try to put a lot of effort in making sure you have examples to help you out. That's why if you have like a PMOS FT, it's probably there's an example. Oh, he didn't challenge me. I want my money back. All right. So there it is. So we'll hit save, save, boom. Okay. So a couple more things, and I'm going to point to the book for these. Make sure you read this, though. And I'm going to go through these really fast because unless you've had a class in layout, it won't make a lot of sense. But it's possible in analog circuits to lay out transistors like this. And again, if you haven't had a class in layout, this won't make any sense to you. But if you've taken 421 or 621, you'll know this is what? You guys are killing me, man. Paulie, it's only been a couple months. Okay, you don't want to put your contacts down because you have these resistances, and you know the resistances change the channel, the voltage that the effective channel sees, and also then the effective VDS, which is right here, drain to source voltage and lambda. This is exactly, and all these discussions are talking about matching. Okay, we'll come back to this one about threshold voltage here in a second. The other thing is, it's possible to lay the transistors out in parallel. What you want to do when you're doing analog designs is the transistors, which these things right here in the middle are the transistors, you want to try to have the same adjacent structure. So you'll often, and they do this all the time nowadays because of the lithography, you'll put dummy structures that don't do anything. They're just there to ensure that this transistor and this transistor see the same adjacent structure, okay? Another thing that's important is orientation. You don't, if you're trying to get good matching, you don't lay out one transistor that's horizontal and the other one that's vertical. Okay? You want them all to be in the same direction, and you also want them all to be as close to each other as possible so they're exposed to the same diffusion and heat sources in the same way. Okay? When you're laying out mirrors, you oftentimes want to split the transistors up if they're really big and you care about matching, so that they're either interdigitated or common centroid. Okay, so here, these two transistors, it's M1, M1, M2, M2, M1, M1, M2, and this is an interdigitated layout. And on the next page, there's some discussion, or later on, there's some discussion, which I'll talk about here in 2 seconds, on common centroid. The other thing you want to do, and this is, I talked about this earlier, you see how this transistor, say, is 20 by 1? And you see how this one is 10 by 1, just as an example. Or I guess it's 20 by 2 and 40 by 2. But you see that there's a little bit of encroachment on these two edges on the width. Okay, and again, we're not doing layout, so if you don't know what this is, I'm not going to test you. If you just double the length like we did here and like we did in the previous example, then the effective W here isn't a ratio, an integer ratio with this one. Does everybody see that? But if I split this device up into 2, so I use M equal 2 instead of just a 40 by 2, now the devices are exactly the same, and so presumably they will have an integer matching of 2. Did that make sense to anybody? Okay, and if you didn't take the 421, 621, I'm sorry, but I still need to cover that because I think it's important, and then you can go back and review it if you take the class, if you can stand me this fall. Okay. All right, so I want to go back and talk about common centroid, and then I want to talk about threshold voltage matching. Okay, so let's talk about common centroid. And what we just saw here is we saw that we had a transistor and we split it up and we had, like, let's just draw it like this. And let me think for a sec. All right, so let's say I connect these all up. This would be, say, M1, and this would be M1, and this is M2, and this is M2. Okay, so you might think, well, I want to just mix them together so if there's mismatches, I get the best match and go M1, M2, M1, M2, and this is called interdigitation. Interdigitation. Does everybody follow? So then the M1s would be tied together, and the M2s would be tied together, and all these would go to ground. Does everybody follow? And why you would want to do that. So if I had a variation, let's say in threshold voltage or size, this would be 1, 2, 3, 4. These would add together and give me 4. These would add together and give me 6. It would be better than putting the M1s right here, which would add together and give me 3, and the M2s together add, and they would give me 7. So the 3 versus the 7, this is closer. Does everybody see? Okay, in math, have you talked about common centroid? Okay, or maybe in electromagnetics. When you have a body or something that you want to balance, you try to find a common center. And one way of doing that is instead of putting the transistors like this, which for me, intuitively, M1, M2, M1, M2, that makes sense. Instead, you break it up so that they have a common center. So this is M1 and this is M2. And if I take and I draw like the like points here, they go in the center like that, and then I would make this M2 and M2, and then I do the same thing. And now when I add 1 and 4, I get 5, and 2 and 3, and I get 5, because I've shared the center. Matching's a really big deal in industry. Okay, I'm not wasting time on it. This is something people spend their lives trying to improve because it improves yield and makes your fidelity of your sound and picture quality and everything better. Does everybody understand this? And when you do this, so this is M, yeah, did I write? Yeah. M1, keep me honest. Okay, so that's M1. So does everybody see if I were to put these on a scale, these would balance, and so would these, and it would balance right in the center? Okay, so I got a question for you. Well, before I do, are there any questions? Okay, if I said that M2 was twice as big as M1, so M2 was twice the size of M1, tell me how I would lay it out for common centroid. How I'd need to have 4 transistors that I connected in parallel, because M1 is 2 and M2 is twice as big. Where would I put those transistors and how would I get common centroid? Yeah, they'd be like this, right? M2, M2. Okay, and then they would be tied here. And then they would again go to the middle. Does everybody see that? Okay, but tell me another way. Oh, wait, does everybody see that? So these two on the edge keep it balanced, and they cross right in the middle. So if I were to go, this was 0, and this was 5, then M2 would now be 10, and twice as big. Does everybody follow? Tell me another way to do the layout in common centroid with M2 being twice as big. Yeah, I could go M2, M2, M1, M1, M2, M2. I don't know. I would say the first one was better, but that's the thing about randomness and matching. It just depends, right, on the process. Okay, any questions on this? We've got one quick thing left. Nope, makes sense? Okay, the last thing I want to talk about is matching and threshold voltage and beta. And actually, since we don't have much time, I'm just going to point to it in the book. Before I do that, if we wanted high speed, how did we select our VGSs? High, right? Does everybody recall that? Okay, if I look at the equation here, before I get into any math or anything, was anybody upset I covered temperature stuff on Friday? You were? All right. Well, you needed it to do the homework, so. Okay, so threshold voltage varies from device to device as well. Okay, so without doing any math, I just want you to think about it and tell me if you are trying to reduce the effects of threshold voltage mismatch. Say one device had a threshold voltage of 0.8 and the other had a threshold voltage of 0.83, because they're not all the same. How would I design? How would I select my overdrive? How would I select my VGS and why? Yeah, you'd want big VGS, right? So if you have big VGS, then this threshold voltage varying minimizes the effect on the ID. Does everybody see that? Okay, so if I go look at the math, and we'll talk about KP. If I look at the math, and I look, and delta V threshold is the variation in the threshold voltage. If that's varying, in this case I said delta V threshold was 30 millivolts. If that's varying, ideally it's 0, so it doesn't matter, then your VDS sat, which we also know is VGS minus V threshold N, or V overdrive or V excess, would need to be really big, and then we would get good matching and high speed by using large VGS, and the drawback would be not as large output swing because the devices would go into triode faster, all right? So you can see the derivation there. Last thing, if you look at similar discussion and you say, okay, how do I, refresh my memory, what is KP? Yeah, mu n Cox, yeah, mu n times Cox is transconductance parameter, yeah. I ideally want to use large devices with a large transconductance parameter. Of course, this thing I can't control as a designer, right? So I can't say I'm going to design with this and change the transconductance parameter because that's a function of the thickness of the oxide used in the mobility of the process. So I have no control over that. It's just, this is where you would see how you would reduce the effects of mismatch in because of the transconductance parameter. Okay, so what I want you to do is go read the first two sections, and when you come back, it would be really nice if you read up through the supply independent biasing, because one of the issues that we're going to have to deal with here is the following. Notice that if this resistor, if I change the power supply voltage, or you can see it here directly in the where I solve for it, you can see if I change the power supply voltage, it's going to directly modulate or change the drain current. I don't want to do that. I want to design a circuit that makes the drain current independent of VDD. Why? Because I don't like listening to the radio and as my battery starts dying like it did when I was a kid, the sound of the radio starts to drop because there's no independence of the power supply voltage. I want my currents and my circuits to be independent of that VDD. Does everybody follow? So it's going to use a circuit called a beta multiplier reference, and we're going to cover that next time on Wednesday. There will be a quiz. You know what to study. Have a good evening. We'll see you on Wednesday.